In this video, we're going to talk about gravity, and through that, we're going to do that through Newton's universal law of gravitation. So with gravity, all objects will pull on. Excuse me. All objects with mass will attract every other object with mass through the gravitational force. So we're used to thinking about this from the perspective of the Earth pulls down on us because we have because we have mass and the Earth has mass. But likewise, we're also pulling on the Earth because the Earth has mass and we have mass. If you're standing in a room with someone, you're pulling on them because you have mass and they have mass through this gravitational force. And in fact, you don't have to be in the same room. If you exist somewhere in the universe and someone else exists somewhere else, you will pull on each other through this gravitational force. Now, as we will see in the equation here in a minute, it's an incredibly weak pull, but it is a pull nonetheless. And this is between every single pair of objects that exist in the universe. There is a gravitational force. Most of that time, that gravitational force is near zero, so we ignore it, but it is technically applied to all things. So the equation that we use for this is Fg equals capital G times m1 times m2 over r squared. So these are the mass of the objects, or the masses of objects that are involved. This r is the distance between the centers of the objects. So this is important because if we're talking about you standing on the surface of the Earth, you're actually very, very far away from the center of mass of the Earth. You know, you're on the surface, the center of the mass of the Earth is in the center. So that's going to matter because it helps keep these from blowing up, right? Because technically, if you think you're standing on the Earth, oh, I'm not away from the Earth at all, so therefore this distance is zero, it would blow out to infinity. This G is the universal gravitational constant, and it's equal to 6.67 times 10 to the negative 11. Sorry, I was mixing that up with a different constant. And the units on it are newtons, meters squared per kilogram squared. So this is where you can see that suddenly most of the forces are very, very tiny, because 10 to the negative 11th is very tiny. So even if you have a really heavy person, you know, a couple hundred kilos, they're standing really close together, you still multiply that whole thing by 10 to the negative 11th, and that eliminates almost all of the meaningful amounts of force. If you're on a different planet, the gravitational force will change because the mass of that planet is different and the distance to the center of that planet is also different. So this is why the gravitational force on the moon is weaker. This is why the gravitational force on Jupiter would be stronger if you could actually stand on Jupiter, but at the surface it's stronger. So you can go through, you can calculate this for any given number of pairs of masses, for distances between the masses, etc., etc.